Welcome once again to our final lecture on machine learning fundamentals. Today we are going to talk about ensemble models. Quite smart technique which enables us to achieve even more results, even better results compared to the single model. So let me share the screen with you. Obviously, as always, you have all the presentations on our shared folder. And let's start with a short recap as always. This lecture is for you. I can't see your faces now, so if you have any questions, comments during my lecture, don't hesitate to interrupt me. It's welcomed. So let's start. Let's start with some short recap of the messages we have, all the information we have covered previously. Firstly, a short recap of the difference between bias and variance. As you remember, we can measure a model quality by comparison between the model, comparing the results of the model prediction, which in this graph is depicted by the straight line with the reality. You can implement it obviously in scikit-learn. The general idea, the most important fact here is that it should be possible to compute as a number. Next, we can do the same also for not linear models. And in one of our cases, I shown you that it was possible to train for the same set training data set, different models. We had the question, which one is the best one? And it appeared that it's not like the polynomial degree is the king. The key is model achievements on the test data set not used during the training stage. So our procedure was firstly split a data set into the training set and the test set, and measure the quality of the model on the test set. And we have identified the following behavior. Apologies for Polish language here, but I think it's quite self-explanatory. On the x-axis, we have the model complexity. For example, for polynomial, that may be the polynomial level 1, polynomial level 2, polynomial level 6, yes, for example here. And we saw that, obviously, the more sophisticated model is, its quality on the training data set is getting better and better. Here we see the error on the training data set, but there is some point for which the complexity of the model, with the increasing the complexity, sophistication of the model, the error on the test set is increasing. So here we have a very simple model. It has quite high error on the test set. Then with increasing complexity, it decreases, but after some point, the more sophisticated model is, the worst result. And we are looking for precisely that point, the optimal model. And we also talked that that model, the total model, this error, the error on the test dataset, not trained dataset, the test dataset can be decomposed into two different values, two components. First component is a bias. The second component, and this is depicted here in blue, the second component is the variance, and this is depicted here in green. And with increasing model complexity, we observe decreasing the bias, which is the systematic error, yes? So bias is this error performed by this person, this guy, yes? He has a quite good hand, but his gun is decalibrated, yes? So the more complex model is, the systematic bias is decreasing, but the hand is very more and more shaky. So when you sum up those two numbers, you get this curve. So this is a short recap. And now that's gonna be the entry point to ensemble learning. Yes, so we needed this recap for cope with the ensemble learning problem. And before we start, I wonder if you are familiar with the concept of wisdom of crowds. How do you understand that statement that the crowd may be wise? What does it mean in practice, the wisdom of crowds? Did you hear about this previously?
Wisdom of crowds? No.
Okay, so as name suggests, the more people you have on board, although each of the guys may be wrong or even stupid, when they make the decision altogether, the final decision may be wise. Obviously, it seems to be a theoretical observation here, but no, it is really grounded in practice. And the first experiments of the type were performed at the beginning of the previous century. And there was a famous statistician, Francois Galton, who made in 1907 the following experiment. He put an ox, this animal, yes, in the middle of the square and asked approximately 800 different people to estimate its weight. Obviously, people were giving very different estimations, from very small, just for a joke, to extremely high, also for a joke, and something in between. But the funny thing is that when you averaged these 800 guesses, you got that number, probably in pounds. I really don't know what's the unit here, when actual weight of the ox was that number. So as you can see, it's 0.1% difference. So this is the example, practical example of the wisdom of the crowd. Yep. Another interesting example, and it is made many times in different lectures. You can watch this video here on YouTube showing the practical implementation of this. Imagine that I had a lecture, I have 300 people. Here it says, let's say it was, I don't remember how many voters, and you ask people in the classroom, the lecture, because we need to have, let's say, more than 100 different people, what's the number of MMMs in this jar? And as you see in this precisely experiment, the lowest guess was 700, the highest guess was 6200, and average guess was 2137 MMMs, while actual number was almost the same. So this is another practical example of wisdom of the crowd. Much more example you will find in this book. If you have some time, it's worth reading. I found also there a very interesting example of the situation when probably somewhere in Italy there was a sinking ship, means continuous time. People were observing in one of the bays a sinking ship from different points of the bay, and after the ship sank, people asked some scientists asked those people who were witnessing the situation to point, in their opinion, on the map where this ship was located during the sinking. And when they averaged this position, yes, they precisely pointed the place when it was in fact later on found. So it's also about the geography, not also the counting, not weight estimation, but also the position estimation. So as you can see, we have many different examples of the wisdom they count. And the funny thing is that you can precisely you can adopt the same strategy for machine learning. And that was the case of one of the Kaggle. No, it was not. It was not a Kaggle competition. It was. Let me check. Maybe I'll find it over the internet because it would be nice to see it in action. Let's ask Google for Ensemble Models history. That was probably the case of competition by. Nope. That was the competition on Netflix. Netflix price. Yep. This is this example. The story was the following. There was a competition for the Netflix prize, as you can see, 207. Yeah, this is the lecture name. And let me check. Yep, the situation was the following. There were many different teams competing for the prize. And at some point of training, there were two leaders. And they were fighting very, very heavily, yes, to improve their results. But they stuck. So what they did, they started forming alliances with some other teams and putting their models together. Yep. And on average, the guesses of those, the average of the guesses of the models within the team gave better results than the best model within a team. So that started, as you can see, that started the history of ensemble modeling. Yes, so as you can see, top contenders for progress prize 207% improvement. So you can see this later on in more details in this presentation. Okay, so let's come back now to the theory. Ensemble learning is a machine learning paradigm where multiple models, often called weak learners, are trained to solve the same problem and combined to get better results. Yes, so you train the same model, the different models for the same problem, and when you combine average, for example, there are many different ways of combination, so I'll show you this later. The results of the ensemble of those weak learners give better results than the best of them. So the ensemble learning hypothesis is the following: when weak models are correctly combined, we can obtain more accurate and or robust models. This is the hypothesis. And definition here, the single weak learner based model is the model that can be used as a building block for designing more complex models. So weak learner will call this a weak learner. Most of the time, these basics models perform not so well by themselves, either because they have a high bias or too much variance. So this is very important to us. The models out of which we would like to combine the ensemble model, that may be a combination either of models apologies, which have high bias, so they are blue on the left hand side of this graph, or have high variance. And the idea is that to reduce bias and or variance of such weak learners by combining several of them in order to create a strong learner. So let's combine those learners. Firstly, let's define the next specifics of the model. We may have either homogeneous or heterogeneous ensemble models. Homogeneous ensemble models are weak learners which are trained using a single base algorithm, the same algorithm that maybe, for example, supervised support vector machine or logistic regression. We can fine-tune the models of the same type, but with the different hyperparameters. So these are so-called homogeneous ensemble models. On the other side, we have heterogeneous ensemble models where weak learners are trained using different base algorithms. For example, the first one will be logistic regression, second one support vector machine, the third one a neural network. Yes, so this is another option. We have it's like different animals voting together, and for the first case we have the same animal like human, yes, but with the different hyperparameters. So this is also very important. From practical point of view, from the implementation point of view, we are going to cover in a few minutes from now. Next, very important fact, in fact, crucial for the distinction of two types of ensembling. The method we aggregate models should be coherent with the weak learner characteristics. So, case number one, if we choose base models with low bias but high variance, so very primitive models, nope, low bias, high variance means that they are very sophisticated models, yes? An aggregating method should tend to reduce variance. So when we aggregate the model, look, this is the high variance model, so this aggregation should reduce the variance, yes? So that should be the method which focuses on reducing the variance. And opposite, if we choose base models, weak learners with low variance but high bias, so these are those good shooters but with the bad gun, they have very, very low variance but high bias. The way we combine them, train them, put together should focus on reducing the bias. Okay, so that's gonna be the first strategy. That's gonna be the second strategy. Here we talk about so-called parallel models, and this is gonna be sequential models. Yes, we'll see in a second how it works in practice. Okay, any questions till now, or it's clear? I think it's not clear till now because we didn't see any practical example, but let's assume that the idea behind is clear. Okay, shall we continue?
Yep.
Thank you. So, two types of guys. This guy has a very low bias, a high bias, low variance, and this guy has a low bias but high variance, shaky hand, yeah? So let's try with parallel methods and train weak learners concurrently. In this method, this is the method applied to that guy on the right hand side. So our goal is to reduce the shakiness of the hand. So at the very beginning we have quite a shaky hand, and later on we stabilize that. So we reduce variance. The first method is called bugging, and under the hood there is a very important technique called bootstrapping. Bugging comes from bootstrap aggregating. So let's talk a few minutes on bootstrapping. Bootstrapping is a very important technique. You'll probably find it also in A/B testing when we are going to perform some statistical tests to verify hypotheses. And in that case, during the experiment design. One of the most important aspects of the experiment design is to choose the appropriate number of test cases to verify the hypothesis on a given what's that name? I forgot the word, apologies for this. Never mind. If you develop the A/B testing, one of the most important techniques during such a development is generating samples of size B. These are the so-called bootstrap samples from the initial data sets of size n by randomly drawing with replacement B observations. So here, let me give you the example. Imagine that we have the initial data set, full data set of 10 examples. And let's say that our bootstrap sample is equal to 5. We can generate a new set of samples by randomly taking those numbers from the initial data set, taking 5 samples, then returning them back, and once again sampling the number 5 randomly. This replacement means that, as you can see, number 4 is both here and there, so we move it back. So this is the technique which enables us to generate many samples from the original data set. The assumptions are the following. The initial data set is large enough to capture most of the complexity of the underlying distribution. So in our case, we'll see it in a second from now, we will have underlying distribution will be, for example, all our customers, and our training data set will be the sample of those customers, like, for example, all those customers for whom we have the history. And later on, when we are going to train different models, we will train those models on some bootstrapped samples of the smaller size taken from this initial data set. But the assumptions should be, and you'll find it in many textbooks on machine learning also, so-called IID, independent and identically distributed. So firstly, identically distributed means that they are representative. The size n of the initial dataset should be large enough to capture most of the complexity. And independence, the size n of the dataset should be large enough compared to the size of B of the bootstrap samples. So samples are not too much correlated. So these are the assumptions. And what's the rationale behind bugging? As you remember, the procedure which ends up with the model is the following. We assume that data contains some patterns. Then we have some machine learning algorithm which looked at this data to identify, to discover those patterns, and then saves those patterns as a model. So in that sense, later on in the production, model is a function. It takes some input and returned some output. So this input, this function is defined with the respect of the training data set. And a training data set is an observed sample coming from a true unknown underlying distribution. So it has some variance in relation to the reality. And we should be aware of this, that, for example, in our case, when we have 1 million customers and we have only history for 10,000 of them, so this sample we have in the training data set is just a sample of the underlying distribution. So this model itself is a subject of variability. If another data set had been observed, we would have obtained a different model. I wonder if you remember the cross-validation. We had the situation where there was a risk that sampling a test data out of the historic data set may impact the model itself, because if we take some sample, the part left in the training data set will generate the model A, but if we set another sample of the test data set, so we remove that data points from the data set, we'll have a different model to fit in. So we decided to make a so-called cross-validation, to repeat the process many times, just to decrease this variance. So bugging is a method which fits several independent models and average day predictions in order to obtain a model with lower variance. So we set these independent models on different subsets, different bootstrapping, bootstrap samples. And now the procedure. Now I think it will be much easier for you to understand if I go through the procedure itself. Imagine that we have some initial training data set. Imagine that we have this problem of prediction of whether the customer will be high revenue or low revenue. And imagine that this initial data set has 10,000 data points. Okay, so this is the starting point. We generate different subsets. We generate L bootstrap samples, like for example, 100, or let's say to simplify, 10 data sets for 1,000 each, yes, randomly. We've return, yes. So we generate 10 different data sets. For each of those samples, we train a separate model. It's like in cross-validation, yes. And then, having these two models, we average those models using the ensemble, and that's gonna be this combination of those weak learners will be our ensemble. So this is a very similar approach to compared to cross-validation. So once again, we train 10 models based on 10 different bootstrap samples of original data set. So let's continue.
I have a question. Can we apply only to the models which use the same learning algorithm?
Yes. Yes, this is, to the best of my knowledge, is for homogeneous models.
I see.
But you can check it. It's a good question. I'm not pretty for 99%. It's gonna be for homogeneous. But just to be checked, okay?
Yep.
Okay. So the procedure: create multiple bootstrap samples so that each new bootstrap sample will act as another almost independent data set drawn from the true distribution. Fit a weak learner for each of these samples. Aggregate them such that we average the outputs. Yep. So this is the procedure. This is the mathematical formulation. And now the most interesting part here is, how do we get the final prediction out of those single predictions? Okay, and now two examples. Let's start with the regression. Just to recall, regression is modeling of numerical variables. So what we predict is a number. Yes, so the procedure is the following: ask each model for a prediction for a new observation. So once again, in practice, imagine that we have problem of price estimation in the housing data set. Okay, so we have created 10 different models specializing in prediction of the price for a given flat with different hyperparameters, with different parameters. So the goal is that when I have a new flat in my database, what I want is the price prediction like? For example, for the flat with the square surface of that level of that size in the given area, etc., is, let's say, 50,000 of US dollars. So we have 10 models. Okay, so we ask each model separately for the prediction and take the average. Very simple thing. Very simple thing. So for regression, there's no sophistication. It's a bit more sophisticated for classification. So now imagine that our model predicts whether there is cancer or tumor on the picture or not. Okay, so this is the binary classification. So our model can give us the probability of that there is a cancer or tumor on the picture. The second probability sums up to 1 that there is no tumor, and the final verdict. Okay, and we have 10 models, 10 different models trained, for example, on different subsets. So we have two strategies. First strategy, so-called hard voting. In hard voting, we ask each model for prediction for a new observation, and we return the class that receives the majority of votes. So if we have some picture, we put it to those 10 models, and 6 of those models said that there is a tumor there, and 4 that there is no tumor, we return 1 because 6 is more than 4. 6 models said there is a tumor, so we return 1. There is also another option, so-called soft voting, which bases on the probabilities returned. So for each category, in our case, this is 0, and the second category is 1. We ask each model for a probability for this category, and then we average those probabilities. And we return the class with the highest average probability, which may give us different results. Okay, so one is based on votes, second one is based on probabilities returned by models. Is it okay?
Yes.
Good. So now, begging for decision trees, because it's a bit more original, a bit more, maybe not advanced, but it has some subtlety worth knowing. So let's start with depth of the tree. If you have a decision tree, as the algorithm, one of the hyperparameters, so this is this knob you can control, yes, is the maximum depth of the tree. So you can control it. If you set it to the low number, you will end up with the primitive model, which has low variance. It's not sophisticated, but it may have high bias. And opposite, if you choose the high value for the depth, you end up with a very sophisticated model. And sophisticated model means that it has, low bias, but high variance. And in the parallel models, we are interested in the second situation, okay? Because as we said, if we choose base models with the low bias but high variance, so this is the case of the deep tree, an aggregating method should tend to reduce variance, which is the case for parallel training. So decision trees deep trees are better choice for packing method because they focus at reducing the variance. So if you meet, for example, bugging method, and you'll have a parameter to control, which is the depth of the decision tree, you should rather put it a bit higher than for sequential models, which will be the subject of the next part of the lecture. But now, look what happens. What's interesting now? Imagine that you have a data set. Imagine that you have a data set. And this data set has, let's say, 10,000 of rows, because we have 10,000 customers in our database. And we didn't speak about this until now, let's say 50 different features. So high number of features. Yes, imagine that this is a churn prediction case. Yes, we have 10,000 customers, and each customer has 50 different features. It's from bank. Yep. So what we can sample when we create the bootstrap samples, we can both sample the records. This is what we started with, but there is also another trick that we can sample also the features. So the first data set would be, let's say, 10% of this 10,000 rows. Yes, let's say we sample 10% of rows, but we can also sample some features. We do not take for this model all the 50 features, but only, let's say, 20 different features. So when you compare this separate data sets here, it may happen that they will have not only the different, it's obvious that they will have different customers here, customer records, but they may also differ in terms of the features taken into account. Yep. So next we train weak learners fitted on a bootstrap sample and ensemble models average of weak learners, which we already did. Why is that important? This is the essence of so-called random forests. Yes. So weak learners are deep trees, not shallow trees, but deep trees. Yes, because this is the parallel training. So the focus is to reduce the variance. Fitted on bootstrap samples and combined to produce the model with lower variance. Sampling is over bootstrap samples and other features keep only a random number of subsets to be done. And the result is very interesting. So that's why random forest is a very powerful. Different trees look at those different models. Yes, tree is a model. Different information to make a decision. So it reduces the correlation between returned outputs. But also, this is very interesting, decision process is more robust to missing data. Observations from the training data set or a new observation with missing data can still be modeled. So, for example, there's a so-called robustness of the model of the missing data. Some models, if you ask them to predict, for example, the price, yes, in regression, or a churn for the customer, if you have some missing value of one of the features, they will generate the error. But random forests probably will not generate. They're robust to this. Why? Because if you have no value for this feature for one of those learners, for this learner which needs this, you will probably find some other learner which was trained without this feature. Yes, so that means that it will be robust. So as you can see, random forest, first you look on different subsets of the data, but also on different subsets of the feature. Okay, is it okay for you?
Yeah, now it's clear.
So the key takeaways for you from tactical perspective. If you wanna fine-tune it by hand, because as I already mentioned, most of the AutoML systems nowadays will do it for you. If you play with random forest, remember that the goal is to reduce variance, so you need to have high variant models. So you choose the high value of the depth, yes, and you may expect the model which will accept the entries records for prediction without some features. Okay, so it will be robust to missing values. So these are the parallel methods. So now let's go to the second type, so-called sequential methods. Sequential. So as you probably remember, sequential methods start with some models which are primitive. So they have low variance but high value, bias, and their goal is to minimize the bias. So this is that case, and it always reminds me, so a few years from now, I was a big fan of how to say it, bow. You know bow? You take an arrow and a bow, you shoot with a bow, yeah? So imagine that you have a good quality bow, but it's decalibrated. So this is your first series, yes? You shoot 5 arrows, yes? And then you look with your, then you check where they hit, and then you see that it's there. So you recalibrate the measurement tool. I don't remember what the name in English, yes? Yeah. And then you shoot the second time. Next, you choose, you check, and you can see that, okay, you have over-exaggerated, yes, to the bottom left. And then sequentially, you achieve your goal. So having the bias kept, having the variance kept, you decrease the bias. Yes, so that needs to be done in sequentially, not in parallel. Yes, so now let's have a look on this strategy as a kind of the meta algorithm. So you start with some initial data set. You train a first weak learner, which is the very primitive model, like for example for trees, this is the tree which has a very low depth. Yes, you train on this initial data set. So it's like the first shoot, yes, first shoot. There is no way of, there's no sense in sampling, just simply take this and you update the training data set in a way to, on the, okay, I will just simply explain it to you now. That's probably better explanation. Apologies for this. Because you update the training data set, that will be much well described here, much better described here. Okay, this is the explanation, the practical explanation. Forgive me for this. I do not want to spend too much time on Fury, so this is probably the good example of this work in practice. Imagine that we have a classification problem. So this is our initial data set, and our goal is to find a line or a curve which will separate blues from reds. So we trained the first model, which is the very primitive, yes? And the results of this model is here in the middle. So our current model after the first training just simply takes a simple line in the middle of our data set and says, okay, everything on the left is red and everything on the right is blue. So current ensemble model predicts the blue class is here and red class. Okay, and then we are looking for the errors. So what we have found is that this dot is not properly classified. Okay, this one. And this one is not properly classified. So what we are doing in the next iteration, we assign a higher values to those 2 points. It's a kind of the, what does it mean to assign the value? For each data point, you can assign a weight, which is a measure how seriously this data point is gonna to be taken in the next iteration training. And then you take such a data set for the new model to train, saying, okay, look, you need to solve the problem. You need to find the curve which separates those two data sets, but look much more carefully on those two data points compared to others. And then you train the next data set. And then you form the ensemble model, which takes the former model and the new model, okay? And you ask this model, combined model for a prediction, you know, those different aggregation methods, yes, whether it's a regression or the classification with soft or hard voting, and you receive the next result. So this is the final result. So this is the result of the combination of this new trained model with the previous one. And what we get here is just a new point which is misclassified. That point was previously correctly classified. Now it's misclassified. So once again, we update the weights of the observations of misclassified points, saying, okay, the next third trainer. Look carefully on this data point. This is the high value you should assign this. Look carefully. Obviously, you take also number. And then you iteratively achieve your goal. Okay, so this is the basis for AdaBoost classification. So if you write those steps in detail, it looks like this: initialize weights of samples in a training data set with d equal 1 over n when n is sample size, so each data point has the same weight. Train the first weak learner, apply weak learner to the trained data set, identify misclassified observations, update weights of these observations in the training data sets, update weights. So instead of all equal, make those data points which are misclassified with the higher weight. Train a new weak learner with a special focus given to the observations misclassified by the current ensemble model. Update the strong learner by adding the new weak learner multiplied by its update coefficients, etc., etc. Repeat. Okay?
Yep.
Good. So there is also a gradient boosting where the ensemble model is a weighted sum of weak learners, and we plan to optimize the weight of each iteration, which may be presented here. So once again, I prefer this picture. It took me some time to generate this. So this is another example of the similar approach. Imagine that our goal is to predict these values. Okay, these are the dataset values. We get some predictions of the current ensemble model are those cycles. And after the first training, we wanted our model to predict this: green, yellow, red, and blue data points. And the predictions, as you can see, are the following. This is the prediction for yellow. This is the prediction for red. This is the prediction for green. This is the prediction for blue. So what we are doing for the next model, we say to the next model, look, we want you to minimize, to train, to predict those differences. Look carefully what's going on this picture, because this is the set of goals for the second model in a row. Look, this distance, look, it's pointing a bit west, mostly north. So this is this direction. Can you see? Green one is here, yellow one is here, and the red one is here. So we train the second model to predict so-called pseudo-residuals, errors of the previous model. Okay, we train this. We combine next the former model with the new one. The new one corrects errors of this one, we combine them, and once again ask for the prediction of our data set. This is our original data set. Can you see? Those crosses are the same like here. And now those pseudo-residuals are a bit smaller, so they obviously form some targets for the third model. So once again, as you can see, this is a clear analogy between tuning your elbow shot after the shot, because each tuning focusing on the previous errors. Look, this is the same situation we had in our tuning here, okay? That was the first error, so the next tuning was focusing on to minimize this error, and we got this result. The third tuning is focusing to minimize this distance, and we get this result. So it works like this, and this is the basis for XGBoost. This is so-called boosting method, yes, boosting, gradient boosting, precisely speaking, gradient boosting. Gradient, which is the difference between the prediction and the model. So in next iterations, we focus on the difference, on the gradient. Okay. Gradient boost, XGBoost, apologies, is also very interesting because it's extremely fast. It has its own implementation in C++, in Julia, yes, in Java. So from the practical point of view, I have, for example, when I install different AutoML solution, I already mentioned to you, like PyCaret or, for example, AutoGluon. Some of them required a separate installation of XGBoost as a library. So it may happen that, for example, you think that you have installed, for example, AutoGluon, and it should work, but you get some compiling results. Why? Because they strongly depend on the separate installation. So, for example, XGBoost. XGBoost is also extremely fast and very efficient. Machine Learning Master, and that's my favorite place where I read machine learning stuff, has a separate book on, this is the gentle introduction to XGBoost, but Jason Brownlee has written a separate book only on the XGBoost algorithm. So I think it's worth knowing. XGBoost has obviously its own website where you will find a separate explanation just for boosted trees. Okay, any questions? So finally, we have a stacking. Stacking methods, I do not have this presentation in the much detail, but the point here for stacking methods is then you can combine here heterogeneous models of different type. So the steps are the following. The weak learners we want to feed. Define weak learners, we define the meta model to combine them. For example, neural network might be the meta model to combine. Then during the training, you split the training data into folds, choose weak learners and feed them under the first fold. For each of the weak learners, make predictions for observations in the second fold. So the combination stage, we feed the meta model on the second fold using predictions made by the weak learners as inputs. So this is a kind of the stacking, and I won't tell you more because I didn't play with that in practice. So when it comes to resources, I have based this presentation on this article. So my credits to this article, which is probably the best introduction I have ever found on the internet to ensemble models. There is also a very interesting Ensemble machine learning with Python 7-day mini course, which is here. It's free of charge, which is also worth trying because it has its own very nice implementation in Python of the toy examples. And in PyCaret, as you can see, you have a separate category of Ensemble models with bugging and boosting. So that completes my presentation on Ensemble models, and maybe you have some questions concerning this.